Okay, let's continue with our infrastructure part of the ENCOR exam. Let's go for 3.2.c. Configure and verify eBGP directly connected neighbors. This is one we have covered so far. So let's go and review the theory first, and then we're going to do a lab. BGP stands for Border Gateway Protocol. It's a standard protocol. It has been categorized as an exterior gateway protocol, or EGP, but more recently, more often, it has been referred to as a path vector protocol. Remember that, path vector protocol. Now, in order to explain what BGP is used for, you should first ask yourself, what are you going to use it for? So most of enterprises use it just to get internet access with multi-homing. Some other enterprises use it to advertise their own IP addresses. Some designs require BGP only at the edge of the network. Some other designs require BGP within all the core network. So, for instance, for enterprises, the most easiest way to reach the internet with a certain level of availability, of good availability, is using something that is known as multi-homing. Perhaps you could negotiate with one ISP to set up BGP, a really basic BGP, and with another ISP also set up BGP. So one ISP could advertise you at the full route, and then the other ISP could advertise you at the full route, so you could decide which path you could use to reach the internet should the other path goes down. Now, you can, for enterprises that are willing to expend more money, they can go and actually buy an IP address or an autonomous system number. So you could go and contract several ISPs to set up eBGP, so you can advertise your public IP addresses using your autonomous system number. So these carriers can also offer you the possibility to not only advertise the default route to you, but also full routing. So this will be a more robust way of doing that. There are other options that you can have. For instance, some service provider will provide you with service that is known as layer 3 VPN that uses multi-protocol BGP. In this case, this solution will help you communicate your headquarters with many other remote offices. In this case, you will be configuring BGP at your border with the service provider, and this will be actually multi-protocol BGP, and then you will be configuring EIGRP or OSPF or whatever IGP within your core network. And then you could do the same. For instance, when connected to the internet, you will use BGP only on the border. But if you are, for instance, a service provider, you will use BGP across all your internal network. You will be using here iBGP and eBGP with your providers and customers. So the type of BGP, whether it is eBGP, iBGP, multi-protocol BGP, depends on what are you going to use BGP for. So let's go for the BGP basics. In this case, this device here wakes up first. So given it is waking up first, it is going to connect through TCP. Is going to try to establish a TCP connection with this other device using the remote devices port 179. The local port here will be a random number, about 1023, for instance 1025. This happens because BGP works over a TCP connection between two devices. So TCP has to come up first. In this case, this device is using this port, and this device is using this TCP port because this device woke up first. In this case, this device wakes up first, so this device will use its port 179, and then this device will use a random port about, for instance, 1026, in order to set up the TCP connection required to run BGP above it. Once the TCP connection is set up, now BGP can kick in and it can send several of these BGP messages, keep alive, just to let the other end know that this device is still up, update to actually send routing information, and then notification messages are sent when something catastrophic happens. So for instance, this device here can notify the neighbor that something catastrophic has happened or is about to happen. So the TCP and BGP sessions must be turned down. Now, the first thing that we have to think when configuring BGP is choosing the autonomous system number. You can go and buy a public autonomous system number if you want to advertise public IP addresses, or you can just choose a private autonomous system number, just as you use private IP addresses to set up and get your network up and running. Originally, this autonomous system number was 16-bit wide. These were the option for public autonomous system numbers. This was the set of available private autonomous system number having 16-bit numbers. Since January 2009, this autonomous system number was became larger, so you can use now 32-bit numbers. This is the set of 32-bit available public autonomous system numbers, and this is the set of ASNs for private use for 32 bits. And this happened because we were running out of these public autonomous system number using 16 bits. Now, what is the format that we're going to use in order to actually express these numbers? This BGP standard has 3 methods, but Cisco only offers 2 methods, two formats: the ASPLAIN format and the AS.dot format. With the ASPLAIN format, we're just going to have a big decimal number, and with the AS.dot format, we're going to break this 32-bit number into 2 16-bit numbers, and we are going to express them as separate decimal numbers separated by a dot. So that is why we are going to call it AS.dot. So for iOS XE, the default is ASPLAIN. If you want to use AS.dot, you can go for this command, BGP as notation dot, and then you have to clear your BGP sessions. And now that you have configured your autonomous system number, you have to think of your router ID. This is a 32-bit wide number expressed as an IP address. It must be unique, and you can configure it manually or select it dynamically. Now, the way that it is selected dynamically depends on your iOS. For instance, for iOS and iOS XE, the highest loopback IP address is chosen, or if no loopbacks are there, the highest up interface IP address is chosen. For ISXR or Nexus, the opposite will happen. We are going to go for the lowest IP address in our interfaces. You can configure the router ID this way. Changing the router ID will reset your BGP sessions. You can use this command to know what is your current router ID. Now that we have configured your autonomous system number, and then after configuring the router ID, you can start configuring your neighbors. In order to configure your neighbors, you need 2 sets of information: the neighbor IP address and the neighbor autonomous system. And for eBGP, this IP address is usually the interconnection IP address, and you have to figure out what is the remote or the autonomous system number that this remote device belongs to. And the opposite will happen as well. When configuring this device, you will have to configure the interconnection IP address of the other side and the autonomous system number to which the neighbor belongs to. So the condition for this to work are the remote IP addresses must match. So this address should be correct, this address should be correct, and the remote autonomous system must match. So this information must be correct, this information must be correct, the router's IDs must be different, and they have to agree on the same BGP version. Some old routers will fail this check because we usually use version 4 of BGP now. So if you have some old routers, it is going to fail this agreement. Now, once everything is set up, now the routers are ready to actually advertise prefixes. We are going to use BGP update messages in order to route by rumor. So this device is going to let its neighbors know about the prefixes this device knows. Using BGP updates, we are going to send the prefix, the length, which is actually the network mask, the next hop, and the other parameters that in this case, this is why BGP is better than other routing protocols, because of the amount of parameters that BGP attaches to the prefixes. Now let's do a real live example. So for instance, let's say that this router here belongs to autonomous system number 10, and within autonomous system number 10, we are injecting into BGP this prefix with the network command. We are going to talk about how to inject prefixes into BGP later on, but let's say that we are using the network command. In this case, this router here is going to set up this update to its neighbor. It is going to include the prefix, the length, the next hop is going to be itself. So it is announcing that this prefix can be reachable through this IP address, which is the interconnection IP address that has with the neighbor. And then the ASPAT, this is a particular attribute that is going to tell you through which autonomous system numbers this prefix has been advertised through. So in this case, given this is the first time we are advertising this prefix, the only autonomous system number that it has in the ASPAT, it is home autonomous system number, which is number 10. And then we're going to set the origin to IGP. IGP happens when you use the network command. This means that an actual human being went in and typed in the network command, making sure it is an appropriate command for this prefix. So it is in this case set to IGP, which means this is a good thing, because this means that an actual administrator went in and took the effort to validate this particular prefix. So IGPs are something that we want. And then this update arrives into this router, and this router is going to process this update, and it is going to change it a little, and it is going to advertise it through all its neighbors, in this case to this device. The prefix remains the same, the length remains the same, the origin remains the same, but the next hop changes, because now it is going to make sure that this neighbor is able to reach this prefix through this IP address. So this device says this prefix is available through me, so the next hop changes for this update, and the ASPAT changes because now this particular prefix has been advertised through these two autonomous system number 10 and autonomous system number 20. So this ASPAT is going to grow as this prefix gets advertised through more autonomous system numbers. Now, this device here is going to receive this update, is going to process it. It is going to also advertise this update to its downstream neighbors, in this case to this device here. This update will have this prefix. It is the same prefix. The length is the same. The origin is the same. But the next hop changes because it is advertising that this prefix is available through this IP address. And the ASPAT changes as well because this prefix has been advertised through this autonomous system, through this autonomous system, and through this autonomous system. So the ASPAT enlists what are the autonomous systems through which this prefix has been advertised through. Now, this other device will receive the update. It is going to process it. Then it's going to try to update its downstream routers, neighbors. And in this case, it's going to prepare this update. The prefix is the same. The length is the same. The next hop changes because it is going to say this prefix is available through me. the ASPAT changes because now this prefix has been advertised to this autonomous system, through this autonomous system, through this autonomous system, through this autonomous system. So now we enlist 10, 20, 30, and 40. The origin is unchanged. It is still IGP, but something happens here. When this device here receives this update, it is going to run an anti-loop rule for eBGP that says that if I receive an update where the ASPAT contains my own autonomous system, I'm going to reject that update. In this case, it is going to change the ASPAT of this update. It is going to see that this ASPAT contains an autonomous system that actually match this autonomous system that is where this router belongs to. So this is a loop prevention mechanism, and it is going to reject this update. Because by seeing this, it will notice that this prefix has been advertised through this autonomous system already. So we don't need another advertisement for the same prefix that has been traveled through this autonomous system. So this is an anti-loop rule. Now let's see the same example. So in this example, we're not going to use the network command. It is exactly the same example. We are going to use the redistribute command. In this case, we are going to set the origin to incomplete. This is a somewhat not so good sign because this will translate into I don't really know where this came from, but we already know that it comes from a redistribute command. So when you see incomplete or the question mark, you have to remember that this was injected into BGP using the redistribute command. This is a more generic way to inject routes, not as good as the network command, but it still works. Now the process is the same. We're going to advertise the prefix, the length, the next hop, the ASPAT, the origin as incomplete. This router will receive this information. It is going to change it. It is going to modify the next hop, the ASPAT, and everything else will remain the same. This example is exactly the same. Notice that this advertise travels as with an origin incomplete. This advertisement. So we also have a withdrawn. What happens if this prefix is no longer available within this autonomous system number? Maybe a link went down, so this prefix is no longer available. So this router here is going to be in charge of sending an update, but with a type of withdrawn. So it is advertising that this prefix with this length is no longer available. So this travel across all the eBGP network. So these devices will eventually know that this prefix is no longer available. Now we can also summarize. We can perform summarization with BGP. In this case, the summarization is not called that way for BGP. It is called aggregation. So let's say that this device here aggregates this prefix here and this other prefix here into a /23 summarization that we call aggregation in BGP. In this case, it is going to add a new attribute, which is the aggregator. So everybody knows in the BGP network that this device, this particular device that lives in autonomous system 20 and that has a router ID of 20.20.20.20 aggregated this prefix. It is going to include this flag that is known as the atomic aggregate. This is used to notify that we are not sending the as set parameter or attribute. When you see atomic aggregate, this means that you are not receiving an as set. Now, if you choose to use the as set, then you are not going to see the atomic aggregator, and you are going to receive also an as set, which this as set is a list of what prefixes are contained, what are the autonomous system numbers that to which the prefixes that conform this aggregation belong to. So for instance, this prefix aggregation contains this prefix here and this prefix here, and this prefix here belongs to autonomous system 10, so this number 10 is included in the as set. This prefix here belongs to the autonomous system 20, so this autonomous system number is included here. So the as set is a list of autonomous systems to which the components of this aggregation belongs to. Let's see how are we going to inject routes into BGP. We have seen many things so far. We have seen how to choose our autonomous system number, then how to configure our routing ID, how to configure neighbors, and now let's see how to actually go and add routes into BGP. So we have mainly three ways: through the network command, through the redistribution command, and through aggregation. So let's say we have this example here. We are running OSPF and as our IGP, and then we have an IBGP session between these two routers, and then an eBGP session between these two routers. In this case, we are going to inject this prefix through IBGP to this device. We are going to inject this prefix through OSPF into this device. We are going to use the network command for these two prefixes and the aggregation command in this device here. And for eBGP, we're going to receive three prefixes. Once that was injected into BGP using the network command, the redistribution command, and aggregation command, and see what are the difference. If we issue this command, we will see the difference. Notice how they have different values for the metric. They have different values for the weight. They have different values here in the path column. They have different values in next hop. Some say 0000. Some others actually say an state an IP address. So what we see an I here. What does that mean? We see a different I here. What does that mean? So let's go into examine this in a fast manner. So let's see what happens if I use the network command. So I have to actually go into the router mode and issue this command network. What is the prefix and what is the mask? So I will be injecting a prefix coming from the RIV into the BGP RIV with this command. In this case, the prefix will be used only if this prefix exists in the routing table. So if I issue, for instance, 10.1.1.0 with a mask of 24, the first thing that BGP is going to do is going to look that here in the RIV. If it does not exist in the RIV, then it is not going to place it in the BGP RIV. This injection only is successful if this prefix exists in the global routing table. Otherwise, it will not work. You cannot inject fictitious, non-existent prefixes into BGP. These prefixes must be learned. They must exist previously in order to exist within the BGP realm. So if this happens, the origin will be set as IGP or I. The path will be source and local. The next hop will be 0.0.0, and the weight will be this number, which is a high number for a weight. Now, if we issue show IPBGP, we can see that the next hop is set to 0.0.0.0. That means that it is local. Metric is set to 0. Local preference is set to known. The weight is this value, which is a high value for a weight. It is a high value. And within the path, we are going to see an I because it is categorized as an IGP origin. We can issue this command for more detail. Show eBGP for the prefix that was injected as a network command. We'll see that the origin is IGP, metric 0, local preference 100. Notice that when you see this empty, it is usually 100, which is the default. The weight, it is a valid prefix, is sourced local, and this is the best. So, okay. Now, what happens if you use the redistribute command? Imports prefix from connected interfaces, static routes, or from an IGP. So if you have a prefix or an IP address that it lives within your router as a static route or as a connected route or a route that you learned from eIGRP, OSPF, RIP, ISIS, or whatever, you can use the redistribute command to inject. Usually these are used for bulk injections. So the network command is usually a per prefix injection, one by one. If you want to inject one prefix, you type in one network command. If you want to inject another prefix, you have to inject another network command. So if you wanted to inject 100 prefixes, you will have to go and type in 100 network commands. So in this case, if you want to do bulk injection, you can use redistribute command. You can use redistribute static to redistribute all your static route prefixes routes into BGP. You can go and type in redistribute connected, and then all your connected networks will be injected into BGP. And you can use redistribute OSPF or redistribute eIGRP to inject all the networks that you learned through these protocols into BGP in a bulk manner. You still can use a route map to filter some of them. And then for static and connected redistribution, you will see this. For all of them, you will see this. And for static and connected redistribution, they will be set as source local with a metric of 0. And from eIGRP, OSPF, ISIS, and so on, they will not be local, they will be just sourced, and the metric will be the same as the metric coming from the routing protocol. So in this example, we have here this connected interface, redistribute connected. So next hop is 0, metric is 0, the weight is high. And then notice that there is something wrong here. This is wrong. This should be this. So this is an example of a redistribution for OSPF. Notice that the metric is no longer 0. This is the metric that comes from the OSPF protocol. The weight is high. The next hop is not 0 because it is not a local learned route. This comes from OSPF, and surely this comes from another router. So this is the IP address that belongs to the other router. And this is, notice that we have here this sign here. It is no longer I, but an interrogation because we did an redistribute command. Now we're using the aggregation. In order for the summary or this aggregation to work, an existing subnet must exist. So for instance, if you want to create this aggregation, then .1.0.0/16, you will need to have a member of this aggregation existing, for instance, 10.1.1.0/24. Otherwise, if this didn't exist, this will not be created. Now, when creating aggregations, and you are going to be origin as I, it will be aggregated local, no metric, and a high weight. So this is the example of an aggregation. Notice the next hop is set to 000 because this is being created locally. High weight because it is created locally. No metric and no local preference. Now, when the routes come from eBGP, the path is set to internal, and when coming from eBGP, the path is set to external. Notice here it is an eBGP route, and here it is an eBGP route. How do you notice this is an internal route? Because at the beginning of the show command, you will see an I here. Notice that you have an I here and you have an I here. These are different I's. This I here means that you receive this route through eBGP. And this I here means that you receive this prefix was originally created through the network command or through aggregation. So this is the origin, and this I belongs to the origin, and this I belongs to whether this was learned through eBGP or eBGP. So you have to remember that. Memorize this. The first I tells you whether this prefix was learned through eBGP, and the last I tells you whether this prefix was learned through the network command, aggregation command, or the distribution command. Now this is a summary of what we have seen so far. Now we have something that is called the BGP state machine. When we talk about when devices get connected together, remember that we are going to run BGP over TCP. We go through several states and that I didn't talk about before. So this is the detail because there are several steps from where we are actually doing nothing to where we are already running BGP. So when we are not actually doing nothing, we are called to be idle. And then when a device wakes up and tries to connect to the other device, this can be in connect or active mode. So in these two modes or states, the three-way handshake is being tried. When the TCP handshake is successful, we go into open send, and then in the open send we evaluate whether we want to become neighbors or not. We are going to check the BGP features. We are going to calculate the hold time. The hold time is usually 3 times the keep alive. And what happens if you configure a keep alive of 10 seconds on one neighbors and you leave the other, or maybe 5 seconds in one neighbor, and you leave the other keep alive as is in the other neighbors, the lowest keep alive is chosen.
We are also going to check here the BGP version, and then we are going to finally land into established. So we want to see established mode always. This is the operational state, and we are going to exchange updates and keep alive and notifications in this state. Now these are the packets that we are going to use: open, negotiates timer, and we are going to use the lowest timers, validate neighbors. Notification is going to send errors. BGP resets after receiving one notification. The keep alive maintains the session alive. Usually the hold time is 3 times the keep alive. In the updates, we are going to advertise or withdraw prefixes. Now we can configure the keep alives this way. By default, remember the keep alive is 60 seconds and the hold time is actually 3 minutes. Now we can reset a BGP session using this command. Always use the soft parameter so you don't kill the TCP session. Remember that we have three actually reefs with BGP. We have the BGP that we usually work with, which is the local in, and then we have a reef for each neighbor. So we have this reef for advertisements that are being received from neighbors, and this reef for advertisements that we are going to send to neighbors. This is a summary of all the attributes. We have seen many of them. We saw origin, we saw next hop, ASPAT, and SSET. We didn't saw local preference, atomic aggregates, aggregator ID, community. And these are, there are others that are eBGP related, so we didn't see them. So origin and next hop, we already saw them. When sending updates, we are going to change the next hop. The next hop changes at each eBGP update. However, the origin is not changed. It is usually, it depends on whether we use the network command, the redistribution command, or the aggregation command, where this value will be chosen from. The ASPAT is a list of the autonomous systems through which a certain prefix has been advertised through. When using aggregation, remember that we can use this flag. When this flag is missing, we are going to also send an as set, and we always use aggregator ID, which it tells us the router ID of whoever aggregated and the autonomous system of this aggregator router. Now, there are some certain eBGP attributes that we are not going to talk in this session because this is focused on eBGP, originator ID, cluster ID. And then we have these two special attributes. So in the case of local preference, you are going to want to modify it when you want to change the behavior of your outgoing traffic. So you have your autonomous system here, and you have several ways to send traffic outside. Then you're going to modify your local preference. The highest, the preferred for local preference. And then for the incoming traffic, you can use the MED or the ASPAT. For incoming, MED or ASPAT. However, you can also use communities, which we are not going to talk about that here. There is another attribute that is known as the AIGP. This is mostly not used. However, it provides a metric when you have a service provider here and you have one office here and one office here, and it provides you an end-to-end metric, but it is not really used. When you're using layer 3 VPNs, it is desired to use the best paths to reach the endpoints of your network. So you can use AEIGIP to maintain a metric end-to-end, but it is ideally it will work the best if you use the same IGP in all your points within all your autonomous systems. However, service providers usually use ISIS, and almost no enterprise uses ISIS, so it becomes complicated to use this. Now, this is the BGP path selection algorithm. This is used if one router receives prefixes from several sources. The router has to select which one is the best path depending on several factors. In this case, 13 factors. And you have to memorize this for the exam. So for Cisco, this is a Cisco proprietary factor. Number one is the weight. If you go to other vendors, you are not going to see weight. Some other vendors may implement another parameter that is similar to weight that evaluates as number one. Then you're going to evaluate local preference, higher is preferred, eIGIP, lower is preferred, although almost nobody uses it. Whether this was logically originated, so we are going to prefer the prefixes that has a local path. For instance, prefixes that we injected through the network command or the aggregation command, or maybe redistribution command of connected interfaces or static routes. Then the length of the AS path, shorter is preferred. Then we're going to examine the origin, whether it is IGP or incomplete. So we are going to compare network command versus redistribution command, MED, whether we learned this from an eBGP or iBGP. The next hop, the lower metric to the next hop is preferred. The older route is preferred. The router ID, cluster ID, and peer IP address. So you will need to remember this. There are some mnemonics out there that will help you remember this. The most common noun is the, I think it goes something like we love oranges as oranges mean pure refreshment, something like that. So just remember that you have to actually memorize this. If you can use mnemonics, just use them. Notice that eIGIP is not generally used, and nobody usually refers to originator ID or cluster ID because these are iBGP parameters. So the exam will usually focus on weight, local preference, locally originated as path, origin met path, probably next hop, and other route. That's it.